Another significant block of problems in section 11.3 are the problems from 9 to 26. Those are all really good ones to practice. When you don't have much experience, that's a lot of work for you to sit there and work through those. So I'm going to go through some of them. One of the main things that I see when I look through here is they're really testing whether you've learned about p-series. And what you're supposed to do is just recognize that when you have a power of n in the denominator, like this example here, all you really care about is if the power is bigger than 1, it converges, and if it's less than or equal to 1, it diverges. When p equals 1, we have the harmonic series. Just reminding you of that name. It comes up a lot. So that's what they expect from this problem in number 9. They're expecting you to look at this, see that root 2, and immediately say, okay, I don't know what root 2 is exactly, but I know it's bigger than 1. So, bigger than 1, converges. That's it. You can say since p is bigger than 1. You can say p equals root 2, which is greater than 1. So it converges. The next one's the same kind of thing, except here, what they do is they try to disguise it a little bit. But we're on to him. We're on to the author here. Okay, so he's doing everything he can to mess with you here. He changes the n over here. Now it's n equals 3. That causes you to think for a second, wait, is that the same type of thing? Now he doesn't have a fraction at all. It's just n to a power. But the negative exponent, you could rewrite that. So let's rewrite it so we don't get confused. N equals 3 to infinity, 1 over n to the 0.999. Okay, now it's in p-series form. The n equals 3 doesn't matter, because all we're really caring about is what's happening at infinity. The first two terms, removing those first two terms does not change anything, so you can kind of ignore this little disguise here. So for this, you can say p equals 0.9999, which is less than 1, and then you go up here, if it's less than 1, it diverges. So this diverges. Number 11 is another disguise. Also, number 11 is red. So I've just noticed throughout that red problems are sort of standard problems. They're not. They're ones that you should know. They might have a little complexity to them, but they're not usually the most complex. And they usually have something important in them for you to practice with. So I really like the red problems in general. I think they signify that there's help online on the publisher's website. That's what the red indicates. But from my point of view, they're just good standard problems. So we have 1 plus 1 over 8 plus 1 over 27 plus 1 over 64 plus 1 over 125. Okay, now it's given in this form. So when you had a nice formula, just look back here. Here we got 1. Okay, yeah, they put a little root 2 there to make it a little bit confusing, but it's basically 1 over n to the p, so you could recognize that. Here they disguised it a little bit by changing it to a negative exponent. And then here in the last one, now you're going to have to come up with the formula. You don't know in advance what that is. If you get that on a test, you just see it as a bunch of numbers. You don't know it's going to be a p-series. Okay, so we have to be a little bit of a detective here. You have to realize that these are all cubes. This is 2 cubed, 3 cubed, 4 cubed, 5 cubed. You might recognize this one and this one a little sooner, but you might have to sit there and think about it a little bit and realize that these are all cubes. So I'm going to rewrite this as 1 over 5 cubed, and 1 over 4 cubed, 1 over 3 cubed. I'm kind of establishing the pattern here. It seems like it's going down by 1, but the 5, 4, 3, and the cube stays consistent. Now it's 2 cubed, and I can even write this as 1 over 1 cubed. So I've rewritten it in a form where now I can recognize the pattern, and with confidence I could say this is 1 over n cubed, where n equals 1 to infinity. Now I've got a p-series, so this converges because equals 3, which is greater than 1. When p is greater than 1, it converges. Move on to number 15. Now we should have confidence that any p-series that we get, we can say whether it converges or diverges. Okay, but here this isn't a p-series. I see the n squared on the bottom, but the stuff on the top is not equal to 1. So what we need to do is rewrite this as two separate fractions. If I write the first one, even though as it stands right there, it's not a p-series, if I combine the exponents, it will be. So let's rewrite this as root n over n squared plus 4 over n squared. Okay, and then we can break that up. The sum of this plus that is just plus, so that's equal to the sum of root n over n squared plus the sum of 4 over n squared. So I'm breaking it up into two p-series, and I'm going to hopefully conclude that both of them converge, or one diverges, one converges, whatever. I'll find out. This is n to the 1/2 here, so I have to subtract a half from the 2. It's 4 over 2 minus 1 over 2. That's a p-series, and p is greater than 1, so this converges. And then I have another p-series. I'm going to pull the 4 out so we can just see it as a p-series. You see the 4, don't let the 4 confuse you, it's just a constant. So every single term is going to be multiplied by 4, and that is the same as just pulling the 4 out in front. This is a p-series where p equals 2, which is greater than 1. So this converges, and that converges. Together they converge. So the original series, now that I've done that analysis, the original series converges. If you look back at all the problems I've done, I've really only used that one fact, the p-series fact, but even that allowed me to do something that looks unrelated and more complicated by that little trick. Of course, somebody has to show you that trick. That's why I'm doing that. And it's hard to invent that yourself in an exam situation. You have to have practiced it ahead of time. Okay, here. Number 17. A good old-fashioned integral test, if you like. So remember that this chapter, this section is about the integral test. So I'm kind of looking out for it, even though the first few that I did there were just p-series. But the way that they show that p-series converges using the integral test. So we're kind of skipping ahead here. This was done with the integral test, but now we get to use that fact, and that gets us a lot of series for free. Okay, now we're going to have to roll up our sleeves and actually do the integral test for this one. I'm keeping in mind this formula, integral of dx of a squared plus x squared is equal to 1 over a inverse tangent of x over a. Okay, if you don't know that, you can look that up in the cover of the book, or you can go back and look at the section where that was covered. Okay, so this one is n squared plus 4, but they're in the opposite order. Now I'm going to do the integral of 1 over x squared plus 4. And I'll do that from 1 to infinity. So that's immediately translated into limit as t goes to infinity, 1 to t. dx over x squared plus 4. Okay, now my a squared is 4, so a is 2. This is the limit as t goes to infinity. When I do this antiderivative, what I get is 1 half inverse tangent x over 2, and then we're going to evaluate that from 1 to t. When I put in t, I have 1 half times inverse tangent of t over 2 minus inverse tangent of 1 half. Okay, so now what happens is inverse tangent goes to infinity. As I let t go to infinity here, inverse tangent goes to pi over 2. And that's this graph here. You can look up the graph on Wolfram Alpha or plot points yourself, but this goes, and try it with the unit circle too. That's an interesting way to do it. So this is pi over 2, and this is negative pi over 2. So as we go to positive infinity, this goes to pi over 2. So as I do this limit, I have 1 half times pi over 2 minus inverse tangent of 1 half. And I don't really care exactly what that is. You could go find that out in the calculator if you like. What I'm interested in is the fact that that is a finite number. And so what we can say is that this converges. And that was what we needed. And it converges by the integral test. Because we say this converges. Let's do another red one here, number 21. N equals 2 to infinity 1 over n ln n. Again, integral test. We need to make, I haven't mentioned this when we're doing the integral test, but to do the integral test, we need things to be positive. I think the first condition the book says is continuous, and then positive, and then decreasing. So if you want to show that everything's decreasing and positive, we have n equals 2, and ln is positive beyond that, and so is just regular n. So this is positive, no problem. Things are continuous. The only place that they're not continuous is at 0, and ln is a continuous function, as long as everything's positive inside there. So this is continuous. Then you might wonder why it's decreasing. Let's see if we can check the decreasing here. So for the decreasing, what I'm going to do is I'm going to look at the function f of x equals 1 over x ln x, just to have a continuous variable there. And I'm going to write the derivative f prime of x. Before we do that, let's write it as x ln x to the negative 1 power. Now let's do the derivative. We get negative x ln x to the negative 2 times the derivative of ln x, and then I have to use the product rule for. So then just write it right here. X times the derivative of ln x is 1 over x. So that's x times 1 over x, that'll be 1. And then ln x times the derivative of x. Okay, so let me rewrite that here as negative 1 plus ln x over x ln x squared. Okay, so you can clearly see that this is a negative value. So this implies f of x is decreasing, because the derivative is less than 0. Look at that negative right there. This is a positive thing for x bigger than 2. And this is something squared, so that's positive, and that's negative. So everything is negative, so it is decreasing. Alright, f of x is decreasing.